Hello everyone, and welcome to Understanding Isotherms, what vapor sorption can and can't tell you. Today's presentation will be about 30 minutes, and it's going to be a jam-packed 30 minutes, I can guarantee that, followed by 10 minutes of Q&A with Dr. Zachary Cartwright and Mary Galloway, food scientist and application scientist, respectively, here at Meter Group. If you have a question for the presenters, type it into the questions pane at any time during the webinar. We'll be keeping track of these to answer during the Q&A, so please don't be shy and submit all of those questions that you have. We'll also be sending out a link to the on-demand webinar as well as slides for you to review as soon as they're available. So without any more ado, I will hand the microphone to Zachary to get us started.
Hi everyone, thank you so much for joining today. Really happy to be here with Mary. Like Brad said, we are here to talk about understanding isotherms, what vapor sorption can and can't tell you. Again, my name is Zachary Cartwright and I'm sitting here with Mary Galloway.
Good morning.
So let's go ahead and get started. This first slide is just an outline. I just want to show you the direction that we're headed today. So we're going to start off by talking a little bit about moisture content and water activity separately, and then show you how we can know more once we combine these two measurements together. Then we're going to be moving through all of the different ways that you can create isotherms, talking about some traditional and classic methods, as well as DVS and then DDI methods. Once we know what an isotherm is and how we can create it, we'll be talking about how to interpret them and use them, primarily in the food industry, but this can also be used in the pharma industry, as well for building materials or even for soil science. So we'll be looking at predicting texture change and also making shelf life predictions, as well as packaging decisions. And then at the end of this presentation, we'll be talking about extracting business value from isotherms. So just going over a few narratives from different companies using isotherms and talking about some of the business value they've been able to get from them. So we're gonna do our best to stick to our 30 minutes. We have a lot to share today, and I'm sure we'll go over. So I hope that you stick with us throughout the entirety of the presentation. So I'm going to hand this over to Mary, and she's going to be talking about water activity and moisture content.
All right, when we're talking about moisture measurements, mostly we're talking about two main things. So the first one I want to talk about is moisture content, and that is a quantitative amount of water. So we're talking about the amount of water in something. This is important for maximizing yield and revenue, because if you can increase your moisture content, water is cheap and you can increase your yield and your revenue. But it doesn't give you a full picture of what's happening, because it is not a process driver, meaning that if we have moisture migration or other issues, moisture content is not going to be able to tell you what you need to know. What you do need to know is water activity. And this is a measure of the energy status of the water. And that is what drives processes to happen. So microbial growth, moisture migration, that kind of thing. So it's really important for product safety and quality. There are limits, especially if you know the food code, where we have to stay under a specific water activity limit so that we make sure our product is safe from microbial growth and things like that. And it also is a good indicator of quality. So if we take these two measurements, what we're really doing is we're finding a target value that the manufacturer is trying to achieve. So if you're just measuring moisture content and water activity, you already have figured out where you want this to be, and then you're just trying to hit that target. So those will either going to come from a regulatory compliance. So an example would be microbial growth limit. So 0.7 here is for mold, 0.85 for potentially hazardous food microbes. The other one is for production specification. But how are those targets determined? So if we are just measuring water activity and moisture content and we plot them together on a graph, we're going to get this one data point. And there is a relationship between water activity and moisture content, but it's not the whole picture. This is just one data point out of a whole moisture map, let's say. So here we're showing that one data point represented on the isotherm, and you can see that it spans a whole range of water activity, but also that is going to influence what is happening or what can happen to your sample. So it's really important to know where on that curve your product sits. If we're getting really close to mold growth issue, or maybe you're hitting a high zone for those browning reactions, we need to know where that is, and so you can avoid them. So another way to think of it too is, instead of thinking of a water activity, it might be easier to think of safety and quality on this x-axis. And instead of moisture content, you can kind of think of that as yield and revenue. So if we can find the sweet spot where your product needs to be, then you can maximize both of these measurements. So next, Zachary is going to talk about the classic ways to create a vapor sorption isotherms.
So the first way, or the traditional way to create an isotherm, is using a series of desiccators or environmental chambers. This is a methodology that I see a lot of graduate students using, but I'm also surprised at the number of companies, even big companies, that continue to use this method. So the way that this works is that you have to determine your equilibrium moisture content at several different water activities, or several different relative humidities. So you might use 6 to 9 controlled humidity chambers, and it's really important to keep these at a constant temperature. And then what you're going to do is measure the weight change until you've reached an equilibrium. So you put your sample in one of these chambers, and then every day or so you have to take that sample out, take a weight reading, and then put it back. And you have to do this over and over until you reach a constant weight. So as you can imagine, this is very slow, requires a lot of labor, and usually you only get a few data points. So here's an example of the data that you might collect from using this method. You'll notice the data points there in red for water activity versus moisture content. And you'll notice that it's really hard to fit any type of model to this data. And this is because there's lots of room for error using this methodology. Now, there's a newer method called the DVS, or the Dynamic Vapor Sorption method. This was actually developed in the early 90s by Pfizer to look at drugs and excipients and to understand their sorption properties. Now, this method is similar to that previous slide, where we hold our sample in a closed chamber and we're still waiting for equilibrium to be achieved. The difference here is that this is an automated system, so it will automatically cycle through new humidity environments depending on the settings that you set up. And this is good because it's faster and you can get more data points for the product that you're looking at. And this is really good for evaluating things like sorption kinetics, or if you're looking at a time-dependent physical change, something like a crystallization. So here's an example of an isotherm that I like to show for spray-dried milk powder. And I want you to bring your attention to the red curve, the DVS curve. So this DVS curve has about 7 points. Again, each of these points has reached equilibrium. So I thought it would be a little bit easier to understand this method if we look at a kind of a clip art image to understand how this data is being collected. So I want you to imagine that you have a closed chamber. In this case, we're at 25 degrees Celsius, but we could look at a range of different temperatures. Now you're going to put your sample in that closed chamber. This could be a food sample, a pharma sample, a soil sample. And in this case, we're at 0.3 water activity. And then underneath this apparatus is a really high precision balance. Now, when running a DVS test, you might ask a question like, how long is it going to take for our sample to reach a certain water activity? So in this case, let's say, how long is it going to take to go from 0.3 water activity to 0.5 water activity? Now, in order to do this, we are going to add wet air to our system. We could do this either direction, wet air or dry air, but because we have to go up to 0.5, we need to add wet air. And this is done by pumping air into the chamber, and this is controlled using an algorithm known as a PID, and then we're able to watch the relative humidity by using a capacitance sensor. So we're going to bring the relative humidity in this chamber to 50%. Now, after an infinite amount of time, that sample is eventually going to come up to 0.5 water activity and come to equilibrium with the surrounding relative humidity. And we know that this test is over by watching the stabilization in the weight. So we're gonna wait until that sample has fully equilibrated, and there's some different measures or different settings that we can set up to know that we have reached that equilibrium. I want you to keep in mind here that in this instance for DVS, the relative humidity of the chamber is driving the change in water activity. And Mary is going to show you a very similar figure for a different method, but this arrow is going to be in the opposite direction. I also want you to keep in mind for DVS that we're equilibrating by weight because, again, we want to look at sorption kinetics and look at time-dependent physical changes. So most pieces of equipment are only equilibrating by weight. We do have a piece of equipment here at Meter that equilibrates by weight as well as water activity, and I'm sure that Mary will bring that up as well. So some drawbacks about this method is that reaching a true equilibrium, this can require an infinite amount of time. There's some things that you can do to speed up your testing process, but as soon as you do that, that starts to bring into question the validity of the results that you're collecting. The other thing is that most instruments only rely on weight, like I just mentioned. So most instruments are not taking a direct water activity measurement, and that means that they're making an assumption that the relative humidity in the chamber is equal to the water activity of the sample, but this is not always the case. The second big drawback is that it's impossible to identify phase changes. So if you're looking for a glass transition point or some type of texture transition, it can be almost impossible to do that using either of these two methods that we just went over. And finally, the third problem with these methods is they don't really represent real world conditions, because in the real world, conditions are usually much more dynamic and not static. And so you're not really collecting data that represents what's going to happen to your product once it leaves your facility. So we're going to talk about a third method now called the dynamic dew point isotherm method, and Mary's going to go over that for us.
So the DDI method, I'm going to use a similar example that Zachary had before. So we have the same setup that we had in the first example. We have our sample at 0.3 water activity. It's in this chamber. There's the high measurement balance underneath as well. And right now it's just sitting there. We're not doing anything to it. So it's going to be driving the humidity inside the chamber. So we're at equilibrium there. So we have 0.3 for the sample and 30% relative humidity in the chamber. So when we're looking at DDI, we're actually asking different questions than we are for the DVS. This is kind of more of an example. How does my sample take up or release moisture in a changing environment? So that's where we get kind of this real world, real-time sorption properties that we're evaluating, right? So we want to know what's going to happen to our sample in a dynamic fashion. So we're going to start our test here, and similar to what Zachary said before, we're going to put wet air. We could also put dry air and dry the sample down, but in our example, we're going to put in wet air. And we start the test by pulsing in some humid air, and we generally specify a flow rate of that humid air. If we increase the flow rate, that means there's more water available in the atmosphere in the chamber, and the sample can take up more moisture. If we slow it down, then we're slowing down that process. And generally we slow it down for more hygroscopic samples and speed it up a little bit more for samples that have a big capacity to take on moisture. And we also set a water activity resolution. And normally we do this at a 0.01 water activity. And that's how the instrument knows when it needs to be taking a reading. So we're going to start our test here. We're going to wait some amount of time. Like I said, the instrument is going to be assessing the water activity and has that resolution that it's trying to fit. So this could be 5 minutes to 2 hours. That's our kind of range of how often this samples. So say the time goes by and now we're ready to take a reading. So everything pauses at this point. We no longer are pumping moist air. We're going to let the chamber equilibrate for the sample and to the chamber. And we're going to take that reading. Now we can see that the water activity is raised by 0.01. That's what we want because that's what our resolution is. And it's also driving that the equilibration in the chamber as well. So you see that our chamber is also at 31%. And we're also going to be taking a weight reading at the same time. So here we're going to use, for the most part, we use the dew point sensor, which is an extremely accurate sensor to do our water activity reading. And in this case, when we're taking that reading, it's the sample that's driving the chamber equilibration. So we're not going to be letting the weight equilibrate. And the reason we're doing that is because we want to exaggerate any transitions that are happening. So we're going to keep evaluating. We're going to have the moisture available as we're running the test. And when we start opening up these binding sites that Zachary will talk about too, then we're going to see a change in that weight, a dramatic change that we can use as a transition point, and that helps us know what's going to happen in the sample in real time. So I thought it might be good to actually show a timed graph of how these two data sets would look. This is for microcrystalline cellulose. On the x-axis, we're just looking at time, and we just ran a DVS and then a DDI because MCC has a really predictable and relationship with water, and it takes it up and releases it pretty evenly, and so we don't really have transitions to look at. So in that sense, this is a little boring, but I think it gives a good representation of what the two styles of data look like. So here, in the red traces are the weight. The blue is for the water activity. In the first section, we have the static DVS, and you'll see that we have lines that show where we're just holding the humidity and the water activity static, right? And we're waiting for the weight to equilibrate. And once that happens, we move to the next point. So you can see how the weight comes up, flattens out, and then we move to the next section. Now, when we do this, it looks like there's a lot of data here, but we're really focusing on those equilibration points. So in a DVS, we really have 10 data points that we're looking at, 5 for the adsorption and 5 for the desorption. Now, if we move over to the right, we see the DDI, and it looks like a nice smooth curve, but actually every one of those is a nice data point. So we can see it in real time as it's progressing through the test. So for DDI, that's actually a patented technology here at Meter Group, where we're going to pass desiccated or humidified air over the sample. And then we're going to track the weight gravimetrically. So we're going to be measuring that and also directly measuring the water activity as well. So we always know both of those values in process. For real-time sorption characteristics, because that's going to help us a lot for some of the applications that we're going to talk about. Get the results in days and not weeks and months. And we're going to have a lot of data points when we're finished with this, with a really good resolution of 01. We actually can increase this if we want. It just takes a little more time. And normally 01 is what we do. So if we go back to the example that Zachary showed before of the spray dried milk powder, we can see here that DVS in the red, but we're also looking at the DDI in the dark blue. And you'll notice that there's 2 transition points. And for spray dried milk powder in particular, we have a glass transition that happens right a little past 0.4, and then it actually goes through a crystallization phase. So if we just relied on the DVS, we would be missing those transitions. All right, so next, Zachary's going to talk about texture change.
Yeah, thank you, Mary. So talking about this dynamic dew point isotherm method, this leads straight into texture change. And as you were pointing out, that spray dried milk powder has a couple transitions. So let's talk about how we determine where those transitions happen. So for texture change, we need to determine what we call critical water activities. These are water activities that you need to avoid in order to maintain your desired texture. So for really dry products, something like a powder, this would be a water activity that you want to stay below to prevent caking and clumping or loss of flowability. But it could also be a snack food product where you're trying to prevent staling or loss of crispness or just loss of your desired texture. We can also talk about higher moisture, higher water activity products, things like baked goods or even cold press bars, things where you're trying to prevent syneresis or loss of desired texture. So it really depends on the product that you're looking at and then the direction of water gain or water loss that you're interested in. Keep in mind here that you do need a high resolution isotherm. You do need that dynamic dew point methodology in order to pinpoint exactly where these texture transitions are. And let me show you in an example exactly why. So this is a texture analysis using a dynamic dew point isotherm, an adsorption isotherm for a powder. So the first thing you'll notice about this powder is the shape of that curve. You'll see that for a very small change in moisture content, maybe a 1% change, you can see maybe a 30 or 40% change in water activity. And a lot of products can have this characteristic. And this is one key reason it's important to measure water activity because of the resolution of that measurement. Now, if we take this isotherm and we look at the second derivative is basically an analysis of the rate of change of the slope of that curve. And what the second derivative allows us to do is identify peaks on that curve, and these peaks correlate to the water activity where the moisture content is changing the fastest. So if we were to click on that peak or highlight that peak, we can see that it's at 0.67 water activity. So this means for this product, this isotherm was done at 25 degrees Celsius. So at 0.67 water activity or 67% relative humidity, this would be the glass transition point for this powder. So let's take a closer look at this isotherm now. So this next slide is the same exact isotherm. And this producer was making this powder initially at a 0.24 water activity. So way down here at this low water activity, there's a limited number of water binding sites. But once you get up to 0.67, this is where a lot of water can start to bind to the product. And as you move even higher up this isotherm, this is where we'll get severe caking and clumping for this product. So if I was working with this powder producer, I might even encourage them to bring up the water activity of their product, because they can safely increase their water activity and slightly increase their moisture content, but still be well below that texture transition point. I put in a couple other examples here for texture transitions or things like coatings and films. So this next example are isotherms for blueberries. And here we're looking at desorption curves. So we're trying to understand how these blueberries are holding onto the water. So if you look to the far right, this curve is for blueberries without any type of film on them. So they have a slightly lower moisture content here at the top. And then you'll notice that they have a critical point of about 0.27 water activity. So this means that once these blueberries are in a relative humidity around 27%, then they're going to have this sudden drop off in their moisture. Now, if we were to add a film or a coating to these blueberries, you'll notice two things. The first thing is that you have a slightly higher initial moisture content, and now this critical water activity is lower. So it's going to take an even drier environment of about 24% relative humidity before these blueberries start to lose their moisture. So I thought this was a really good example if you're thinking about trying to keep water inside of a product. Now we can look at the exact opposite, trying to keep water out of a product. So this is an example or some data that was collected for seeds. So in blue, you're going to see uncoated seeds where water is able to penetrate into those seeds, and you have a higher moisture content at the same water activity compared to seeds that have different coatings. So whether you're trying to keep water in a product or water out, isotherms can be a great method for understanding how effective your coating or your film is working. Next, we're going to be talking about shelf life and choosing packaging. So I'm going to hand this back over to Mary.
So I thought it might be a good idea, because I do get this question quite a lot, how to actually calculate a shelf life. So in the calculation, it's going to take into account the sorption properties of the product, so the isotherm in particular, the storage conditions. We need to know what that product is going to experience, so temperature, relative humidity, atmospheric pressure. And lastly, the packaging. So for this, we need surface area, mass of the product in the package, and the very important water vapor transmission rate. So packaging is what is going to protect your product from the outside conditions. So if you have good packaging, it's going to limit the vapor that's able to go through. So let's get started on how I actually do this calculation. So I start by generating an isotherm, and this is an isotherm for granola. And in particular, I'm interested in the adsorption only. So I've made this file of just the adsorption. Now I want to know for my product, for a granola bar, that is going to, the shelf life is going to be limited on its texture change. This is a crunchy granola bar, and we don't want it to stale or get soft or whatever. So it's going to be texture that's going to be what is going to end our shelf life. So when we look at this, isotherm here, it might be difficult to be able to figure out any of the specific transitions that are happening. So what we use is the Svidsky-Golay second derivative. And basically it's evaluating the slope change and highlighting those in peaks and valleys in this lower graph in the blue. Now, I get this question quite a bit too, because you'll notice that there's two peaks, and peaks means that there's an uptake in water, right? We're increasing the moisture. And I get this question, which one do I choose? There is the smaller one that's around a little past 0.4, and then there's a bigger one past 0.7. The tendency might be to pick the higher one, but really we want to know, when does it transition first? So this water activity of this granola bar natively is about 0.2. So whereas we're moving up and increasing in water activity, we want to know, when is it first going to hit that transition? So I want to use the first transition. And the first transition is right there at 0.42 water activity. So that's the one I'm going to be using in my calculations. I'm not going to use the bigger one, because by the time we get there, it's already had a change. All right, so this is the calculator that we use here at Meter. You can see some of the information. We're going to go through a little bit of what I talked about before. So for my granola bar, it's going to be the humidity I picked at 65% relative humidity. We've got sea level atmospheric pressure at 100 kPa, and my temperature is going to be 25 degrees C. Now for this is just a little granola bar, so we've got a very small sample, 35 grams. The packaging is, the surface area for that also is quite small, but we're in meters squared, so that all is good. And then I chose 1 as my WVTR, which is actually pretty good packaging in grams meter squared per day. And then we're going to start with the initial water activity that I talked about. So where it natively starts is at 0.20. And then the critical shelf life. That's where the water activity, once it hits that point, it would end the shelf life. Now I put, pardon me, I put 0.42 because I wanted it to be easily tracked. You could see where I was getting that data point. I would agree with Zachary that I probably wouldn't actually put 0.42, because by the time it hits this, it's already starting to transition a little bit. We don't want it to get that close. So I would recommend dropping this critical water activity down a little bit, maybe to 0.4 or maybe 3.8, something like that, just to make sure that we're not getting close to that transition. But for this example, we're going to keep it at 0.42. The other thing we're going to put in here is the isotherm. And I realized I forgot to mention, when I was doing the evaluation, I actually trimmed the isotherm down. Let me go back, just, boop. Oh, it skipped over one of my slides. Apologies there. So after we get this point, I wanted to mention this, which is where we need to check the model fit. I apologize. Somehow it jumped over the slide. Because in the calculation, we're going to model the data. That's how we need to have the data in that format so that it can use the calculation. And in this isotherm, I've trimmed it. You can see that it doesn't have the higher water activity. I'm going to focus on the area where I'm interested in, so the range of water activity I'm interested in. And I want to make sure I'm modeling it really well between where it starts and the 0.4 where it's critical, so I can get a good representation of that data. So we'll look here. We like to use the DLP, which is a double log polynomial. And we have a really great R² value here of 9996. So it's a really great fit. You can use other modeling equations like the GAB or the BET. There's some limitations to those. But in particular, what we really are caring about is getting a good fit to the data, because that's how it's going to predict it well. So it doesn't really matter what it is, as long as it's going to model your data correctly. Okay, back to where we were. Now, when I put this isotherm in, I'm going to put in the trimmed one. I want to put in the one that's going to have the really good model fit. And then from here, I'm going to calculate the shelf life. Now, when I do that for this granola bar under these conditions, the shelf life is 151 days. That's about 5 months, so that's not too bad. But let's say that's not quite where you're hoping for. Maybe you're hoping for this granola that would be a whole year. So how do we figure that out? What can we change? And in this case, it's really easy. What we would change is the water vapor transmission rate. So we can use this to determine what kind of packaging will give us the shelf life we need. So this is a similar calculation, but now with the same data that we put in before, but now instead of the WVTR, we're actually going to put in the shelf life that we're looking to get. All right, we're going to put that same trimmed down isotherm that has the good model fit. Push calculate, and now we know that if we have a WVTR in our packaging of 0.42, that it's going to give us this whole year shelf life under these conditions. And that's very similar to what would be like a foil line packaging. So this tracks very nicely. Next, Zachary is going to talk about the business value for for isotherms.
All right, so this is just the last section here of our webinar today. There are lots of different ways that you can get business value from isotherms, and we focused a lot today just on texture and shelf life, but I tried to summarize this in 3 key points, the ways that I see clients using isotherms. So the first one to add business value is simply to maximize your moisture content for profit. So you can use an isotherm to understand the maximum amount of moisture that your products contain while you maintain your quality and your safety. So while maintaining your ideal texture or preventing certain chemical reactions or reactions from occurring, and also keeping the safety and staying below your microbial limit. A lot of products are sold based on weight, especially in the food industry. And so the more water you can sell, the higher your revenue. It's pretty straightforward. Water is the cheapest ingredient in your formulation. So if you're able to increase the amount of water, this can help to increase your revenue. So here's an example of how you could do that. The first step is to set your guardrails. And what I mean by that is to set your acceptable water activity and moisture content ranges. So this is an example for cannabis. And here we're looking at the desorption curve. And this has an ideal water activity between about 0.56 and 0.363 water activity. And we know this because for this specific product, if you go below that water activity, this represents lost quality. You start to lose terpenes, and the quality of that bud is not the same. If you go higher than this water activity, this represents lost safety. So this is a region where you can start to have mold and microbial growth. So once we've set our ideal water activity range, and if we use the desorption isotherm, then we can relate this back to moisture content. And this is important because anything less than this ideal moisture content represents lost yield and lost revenue. So by using this isotherm and by having some knowledge of water activity, we're able to find the sweet spot for optimizing all of these things that we want to consider. Now, the second step is to reduce variation in production. So once we set that target moisture content using our isotherm, then it's really important to start increasing the monitoring of your product during production. So this can result in 3 things: reduced variation, an increased moisture content, and also safer products. So let me show you exactly what I mean. Here's an example where the average moisture content is right there at 9%. We're looking at about a plus or minus 1% variation. You'll notice that some of the products are going over their safety limit, as well as this wide range in production. Now, if you start to monitor this and increase your moisture content, your results may look like this. So now you have an average moisture content of 0.95%, a smaller range, maybe plus or minus 0.5% moisture content, and you're also preventing some of your products from going above that safety limit. So let's look at a real world example. This is a business value example for a pet food company here in the States, and it has a really big annual production. And when we first started working with this company, they had a moisture content target right there around 10%. So by looking at the isotherm and setting a new water activity target, we were able to show this company that they could be producing at 10.4% while maintaining their safety and quality. So just a small change in moisture content, but let's look at the financial impacts. So here's an example of a graph very similar to the last slide, where you can see the increase in moisture content, the reduced variation, and it doesn't show it as well here, but also preventing products from going above their safety limit. So because this company was able to start replacing their raw materials now with water, they have a lot of raw material savings, and because they're paying a lot for the raw materials or for the ingredients, after a year, they had about an annual yield increase of over $1 million for this product or for this formulation. So I really like this example because it shows how a very small change in moisture content can have a huge impact on the finances for a company. The second way that isotherms can add business value is by accelerating formulation processes and also reducing R&D costs. So I'm glad that Mary went back and showed you the modeling, because that modeling can be used to quantify moisture migration of a new product, visualize a new recipe's isotherm, and also predict the equilibrium water activity. So all of these things can be done before even making that final product. It just requires that you have an isotherm for each of the ingredients. So this is an example using the DLP ingredient mixing tool. And in this case, we're going to look at cold press bars. So imagine that you're making a cold press bar. We're just going to use 3 ingredients here to keep it simple, but you could add as many ingredients as you want. So here we're looking at date paste, blueberries, and cashews. You just have to put in some information about their water activity, their initial moisture content, and then you can also add a mass. So this allows us to look at different mass ratios. When you come in here and hit calculate, it's going to show you the isotherms. So here we have the isotherms for the date paste, the blueberries, as well as the cashews. And using this information and by modeling this, we can get a combined isotherm. So we can start to understand that final product before we even make it. And we can also get an equilibrium or a final water activity. Down below this graph, there's some additional information. You'll see the final water activity again, as well as the coefficients for the isotherm. So these coefficients, these were shown on the screen that Mary brought up before for the modeling, but these coefficients can actually be used in the shelf life calculator that Mary was showing, so that you can even predict the shelf life and start to think about your packaging needs for a product that hasn't even been made yet. And then finally, over here to the right, this is just information about the moisture content, so you can understand the direction that water is moving between your ingredients. Here's an example or a narrative from a company using this type of technology. I hear this all the time from R&D scientists. It's simply taking too long to bring new products to market. And so by using isotherms, you can understand these products much quicker and understand problems that you may run into, but before they occur. And the business value here is simply being able to release products faster. So from this specific company, they said that they could release their products about 5 times faster, going from about a 5-month production time for a new product to a 1 month. And in many cases, this allowed them to be the first to market for new products or new flavors. All right, finally, the third example of bringing some business value to your company using isotherms is simply being able to relax and know that your product is going to be able to maintain its safety and quality once it leaves your facility. So isotherm analysis allows companies to prevent unwanted texture change, like we've gone over, avoid recalls, especially due to microbial challenges or microbial problems, and also to make those shelf life and packaging decisions, again, like we went over before. So just a quick narrative for each of these. The first one is for a protein powder company. We see this all the time. A lot of companies really struggle with caking and clumping or loss of flowability. In this case, this company was having about 5 to 10% of their total production having this problem. The result was that they had to either rework this product or get rid of their product, and their reputation was hurt in many instances. The solution here was that they started using isotherms. They understood that they were producing way too close to their glass transition point. And by having this information and by using isotherms to make the correct packaging decisions, they now have less than 0.1% caking. So this issue was costing over $500,000 in lost product the year before, but now really reducing that by having the right type of data and insights. The next example is for a healthy snack food company. This company was having a recall due to mold complaints by their customers. So we looked at this product and in doing an isotherm analysis, we were able to see that a temperature around 35 degrees Celsius was actually causing the water activity to exceed 0.7. So if this company would have used isotherms before, they could have really understood the relationship between water activity and temperature. So now this company is using isotherms to set their product specs and also understand exactly what temperatures they need to avoid. This first recall cost over about $750,000, and this is something that would be completely preventable if the R&D team would have had these insights ahead of time. And then the last example is for a packaging company. So this packaging company was working with a client who wanted to use a more environmentally friendly packaging, and they were able to use isotherms to quickly understand the water vapor transmission rate they would need in order to maintain a desired shelf life. So this is really nice because this company could help their clients switch their packaging with confidence and save them a lot of R&D time and avoid having any issues down the road. So I see this a lot, especially now, companies changing packaging, whether it's due to wanting something more environmentally friendly or having problems getting the packaging that they need, and they have to shift to something new. So we're just going to end here with a summary, and I'll let you go over that, Mary.
Yeah, so hopefully you feel like we've discussed why moisture content and water activity together can give you a lot more information than just one data point if you're just taking a reading of either of those. Hopefully you now understand the ways you can create an isotherm and can start to think about how to interpret and use them. And surprisingly, even though I know this is really long, a lot of information, Zachary and I didn't even go over all of the things you can do with isotherms. So check out our website and you can find out more product-specific stuff or reach out to us. But we wanted to focus on predicting texture change and doing shelf life predictions because those are the #1 questions that we get. And hopefully you've also been able to start thinking about how to extract some business value from the isotherms. Now, Zachary, you have a podcast. You want to tell us about that?
Yeah, I just wanted to take a moment to bring this up. I do host a podcast called Water and Food. If you're interested in learning more about the business value and how companies are using equipment or technology from Meter Group to be successful, this is a great way to highlight success stories and look at different products. I think we've done chocolate, mushroom jerky, cannabis, candy, and so on. There's so many, I can't think of all of them right now. Right, pharmaceuticals. So the list goes on, and we're always also looking for people to be on the podcast. So if you are working with something really interesting, or if you're trying to tackle a specific challenge for your food or pharma application, we would love to hear from you. So I just wanted to take a moment and plug the podcast. Please like and subscribe, and maybe even reach out to be on the show. So we just want to thank you so much for attending. I know this was a little bit of a longer webinar, but we do really appreciate your time. So thank you for being here today. And we'll just end, here's our contact information. You're welcome to reach out directly to me or to Mary. There's our phone numbers and our emails. Again, like Mary mentioned, you can go online and visit us at metergroup.com. We just have a brand new website that was released, and so please check that out. We have lots of other webinars that are on there as well if you'd like to go back in time and see some of the other things that Mary and I have worked on. So thanks again, and we're going to open this up for questions.
Yeah, we do have a few. We, like Zachary said, we are a little bit over time, but we would like to use the next couple minutes to take some questions from the audience here. Thank you for those who have submitted your questions already. There's still time to submit them if you'd like, and we'll try to get to as many as we can before we finish. We'll probably take a few here. If we don't get to your question, it is being recorded, and so our presenters or somebody else from our Meter Food team will be able to get back to you directly via the email you registered with to answer your question. So don't worry, submit all your questions and somebody will be able to get back to you. All right, so our first question today. So Mary, thank you. Mary, you talked about your trimming data, so trimming the isotherms. Is that something that you can do within the software, or does that need to be an external program?
No, it's in the software, which is very nice. You don't have to export. You can, but you can do a ton of stuff within the software. And so to trim your data, to figure out those model fits, to generate the transition point, analysis, all of that's in the software. So it's very nice. You don't have to export it and rework it all in Excel.
All right. Okay, that's good to hear.
Yeah.
Everything's there. All right. Let's see. Here's another one. How should an isotherm be created for bread and cake products if there's a moisture migration from crumbs to crust, while the percent moisture content remains stable if it's taken as a whole because of good packaging material, that kind of WVTR. So.
Want me to take it?
Yeah, go ahead.
I can take it. That's a really great question because there is moisture migration within the product and eventually that equilibrates out. But if you're having a problem where that is undesirable after it's packaged and that once it's hit that equilibration, what we can do and what I would suggest to run the isotherm is actually pull those apart, and you can run 2 different isotherms on the crumb and the crust, and then you'll be able to see where the critical points are individually, and you can hopefully be able to formulate. I mean, it'll take a little bit, but you can formulate those to where they end up as an equilibrated product that both of those are happy. And you can actually kind of use probably the mixing ingredient example that Zachary had for the bars in this case.
All right. Okay, this one is a good one. This is kind of a bigger, deeper dive. And there are some other questions that kind of flow into this, but this basic one is just asking, does isotherm-based critical water activity for powder caking, or this can be for any other product characteristic, how does this correlate with human sensory observations? So we have a lot of our clients or companies that we work with, or even prospective clients where they say, hey, do we really need isotherms? Like we have a really good trial and error method where we can kind of get a feel for how things are supposed to be, look, taste, that kind of thing. Can you dive a little bit into that?
Yeah, sure. So I think you could save yourself a lot of time if you just start with the isotherm and identify that critical point. We've done a lot of analysis where once we identify the critical point, let's say for a cocoa powder or something like that, that we've also will hold that powder at the relative humidity that will cause that texture change, and then those have been served to like a sensory panel to see if they can notice a difference in usually it lines up perfectly. So we do see a correlation between the sensory panel and then holding the product at that critical point. So for the most part, what I've seen is there is a correlation. And if you start with the isotherm, I hope that this webinar shows you that using the dynamic method, you can pinpoint and exactly know the temperature and the relative humidity that's going to lead to a critical change or a texture change or whatever type of change you're looking at for that product. So I think you can save yourself a lot of time just by starting with the isotherm. Is there anything you'd add, Mary?
Well, the only thing I would add maybe is, we showed that moisture map in the very beginning where it shows how water activity is related to and exacerbating some of the processes that can happen. So if you kind of know where you're at and know, you can kind of take all of that information to account, right? You can run the isotherm, get the critical water activity, maybe lipid oxidation is a problem for your powder or a browning issue, right? And then you can kind of put all of those bits of information together to try to formulate something that's going to have long stability.
All right. Okay. I think maybe we'll do one more. We're over time, but we do have a bunch of questions that we are not going to get to. Again, Zachary or Mary or somebody else from our Meter Food team of experts will be able to get back to you and answer your questions. So this last one, any suggestions for hardening of protein bars in related to moisture content and water activity? Just keeping in mind a good shelf life.
Yeah, so if you're getting hardening of your protein bar, you're probably losing some moisture from that bar. And this may be something that we want to look at with a desorption curve to understand if, kind of like if you remember that blueberry example, there is a critical point where you start to lose a lot of water from that product. And it may be similar for this bar where you're just reaching a critical point as you desorb that you need to stay above. So even though a lot of what we looked at today was adsorption, even in the shelf life calculations that Mary looked at, we can run this in the opposite direction. We can use a desorption curve and then assess different conditions and how that may result in water being removed from your product. So either direction, adsorption or desorption, picking up water or losing water, we're able to look at that. We just need to run the right test and collect the right data.
All right.
I
Okay.
agree.
All right. I think that's going to do it for us today. Thank you again. There are a bunch of other questions, really good questions about specific processes and products, comparisons between DVS, DDI. Again, somebody from our food team will be able to get back to you and answer your question directly. Thank you again for joining us today. We hope that you enjoyed this discussion as much as we did here. And thank you again for all your great questions. If you would like to know more information on understanding isotherms or would like to talk to us further, please consider answering the short survey that will appear after this webinar. Also, you can visit us at metergroup.com, like Zachary mentioned. Also, look for the recording of today's presentation in your email and stay tuned for future Meter Food webinars. Stay safe and have a great day.